Okay, we have some more on probability theorem, fundamental principle. This is a basic principle of probability. Let's say we have uh, the number of different computational methods for the event A is m, and the number of different computational methods for event B is n. Then we have the total number of different computation computational methods for A and B is m by n. That means we have m n instances of the of the instances of probability when you are dealing with those events A and B. For example, let's say I want to make a password for logging some portal site. Then, for example, we have two alphabet and two numbers when you make your own password, and the order is preserved. So alphabet, number, number. So the total number of alphabet multiplied by the same thing, and the total number of those number between 0 and 9. The number is 10. So we have a 26 alphabets, 10 numbers, and 10 numbers. So you multiply all together, that come up with the 67,600. And this multiplication is based on the concept of this fundamental principle. Now, from now on, we are dealing with factorial computation. So sometimes we are trying to find the not exact n factorial, but the approximation of n factorial. This is the theorem of Stirling's formula. So here, n factorial is approximately close to square root 2 pi multiplied by n, which is the natural number, a natural number, n to the n plus 1 over 2 multiplied by exponential to the minus n, because this number is huge, so we will take logarithmic function with base 10. So log n factorial approximately equals to 1 over 2 multiplied by log 2 pi plus bracket n plus 1 over 2 log n minus n log e. So this is the approximate number of n factorial. Okay, more on probability. Theorem, permutation. We can think of permutation without repetition. So we have n different and distinct object. From those n objects, we don't allow repetition, and we consider the order and pick all objects from those different n object. What is the instances? The number of instances. There will be permutation, and here we have p subscript n r, which is defined as n factorial over n minus r factorial. This is the uh, concept of permutation. For example, if we have 4 by 4 puzzle, I think you remember this puzzle in your computer, or we have some toy of this 4 by 4 puzzle. And here we have 16 tiles, but one of the tile is missing, is blank. So actually it has 15 tiles, and we slide horizontally or vertically in order to uh, arrange those numbers in order from 1 to 15, because we have one blank. Or you you find the nice figure or picture for that puzzle. So the number of that 4 by 4 puzzle is 16 factorial, which is a huge number. 209227898888000. So this number uh, uh, represent this permutation. So n is 16 and r is also 16. So 0 factorial is defined as 1. So 16 factorial divided by 0 factorial. Okay. Okay, we have another theorem. Theorem, Maxwell-Boltzmann distribution. So I will use MB distribution. This is some kind of permutation with repetition. So repetition is allowed. You can put those objects back into the box, and you can draw once again. So n different and distinct object you have in the box, and you pick R object, but repetition is allowed. So you can put you selected one object, then you can put this thing back to the box. So what is the instances? What is the number of instances of that permutation with repetition? This is very simple. N to the power of R. So you, among n distinct object, you pick R with repetition allowed. For example, in DNA coding, we have 4 kinds of key nucleotide: A, G, C, U. That is adenine, guanine, cytosine, and uracil. Sometimes uracil is replaced by thymine. And by using those 4 nucleotides, we are trying to make and form 20 kinds of amino acid. Then what is the smallest length of this nucleotide? So we have 4 different and distinct object here. So n is 4, and this in this case replacement is possible. So 4 to the r is greater than or equal to 20 kinds of amino acids. So simplifying this, r is greater than or equal to log 20 over log 4. So r becomes 3. So the smallest length of that integer will be 3. Now we have some other distribution. Theorem, Fermi-Dirac distribution. I will use FD distribution. This is combination without repetition. So among n different and distinct objects, we don't allow repetition, and the order is not important. And to pick up R object of combination, what is the number of instances? So I will use a combination with a round bracket over there. So round bracket NR, which is the same as combination symbol C. Left hand side you have a left subscript N, and the right subscript you have R, which is N factorial over R factorial N minus R factorial. So for example, in APEC Congress, we have 8 political leaders, and they are trying to shake hands with each other. What is the number of instances? So that means we don't allow repetition, but we are not, the order is not important, because two guys meet together and shake hand, then the order is not important. So this is combination 8 2, so it will be 8 factorial over 2 factorial 6 factorial, and this is equal to 28 instances. By the way, this Fermi-Dirac distribution follows quantum physics, and if you remember the atoms and electrons, you go further deep and find the smallest particles. We have fermion, which the name is from Fermi and Dirac. So this in this smallest particle is called quarks and leptons. By the way, lepton is electron, muon, tau, etc. Quark has different names. So the total, we have 6 quarks and 6 leptons. So this particle called the fermion will make substances in the real world eventually. So this statistics will follow Fermi-Dirac distribution, combination without repetition. Now we have theorem, Bose-Einstein distribution, BE distribution. This is combination with repetition. We allow repetition. So among n different and distinct objects, we allow repetition, and we don't think of the order and pick R object. What is the combination of that that instances? So this is combination because we don't consider the order. So combination n plus r minus 1 r. So this is defined as n plus r minus 1 factorial over r factorial n minus 1 factorial. For example, if we have 3 different variables in our analytic function f, what is the different computational, the number of different computational methods to find the 6th order partial differential equation? What is the number? So here we have n equals to 3 because the number of variables is 3 for x, y, z, for example, and 6th order partial differential equation. Here we have del x, etc., del y, del z, etc. So we have a 6th order partial differential equation. So R is 6. For example, we are dealing with we differentiate with respect to x twice, and for with respect to y 3 times, and for z one time, just one time, then del 6 fx comma y comma z over del x square del y cubic del z. This is the partial differential equation. And what is the number of instances? That's combination 3 plus 6 minus 1, because n is 3 and r is 6. And you pick up, select 6 of them. So it's 8 factorial over 6 factorial 2 factorial, which is 28 cases. By the way, this Bose-Einstein distribution is from also quantum physics, and those particles which actually convert energy is called maybe transmitting energies. These particles are called the boson, and in boson we have a photon and gluon and Higgs particles together. So 5 of them discovered so far, and those bosons follow the rule of Bose-Einstein distribution. Okay. So, in summary, we have 4 kinds of permutation and combination altogether. So, if on the left hand side, the column, we are think of the ordered case among n distinct or distinguishable object. We consider the order. On the right hand side, on that column, we have indistinct or indistinguishable, so the order is not important. And the first law is we don't allow repetition, so we don't have any replacement. But second law, at the bottom, we allow repetition. You can replace the selected object back to the box. Okay. So on the left hand top, we think of order. Order is important, and distinct among n distinct object. We pick R object. So this is a permutation n R. And left bottom we have n to the power of r, which is MB distribution, Maxwell-Boltzmann distribution. Among n distinct object, the repetition is allowed, so it's n to the power of r. On the right hand side, right top, we have a combination. The order is not important, and we don't allow repetition, so this is combination. So among n object, you pick R object in the box. So it's combination n R, which is called the Fermi-Dirac distribution. And right bottom, we have a Bose-Einstein distribution. Order is not important, but you can replace the object back to the box. So it's combination n plus r minus 1 r. And this is basic principles of how to find the number of instances when you're dealing with those probabilistic concepts.